this video, I'm going to show you how to use the CubeSat Thermal Power Toolbox for running thermal and power preliminary analysis for CubeSat. After opening the tool, we can see that we have 4 tabs. We start by defining the orbit. To do that, we can choose between Earth and Moon. Okay, on this example, let's do a moon example. Okay, so you can see we select the central body moon. We then enter the solar flux in watts per meter square. We select albedo. These two consider a constant albedo across the entire surface of the planet. For the calculation of the IR, we can choose between day and night temperature. In this case, we select the temperature for the daytime and the nighttime. For the moon, we have a very big gradient there. The default value is 350 for the daytime, the nighttime 90 Kelvin. For a more accurate simulation, we can also do the gradient. On this case, you only need to put the nighttime temperature, and we're gonna run, in this case, a gradient temperature from the sunlight point where the sun is shining on the surface, gets really hot, and the temperature gets decreased as we move towards the terminator line. So let's run this gradient. Then you select the epoch time. Here's today, how many hours. So we can put like 12 hours. Then we have the orbit parameters here, semi-major axis. We can do a low moon orbit, inclination 90. Let's do ran true anomaly. You select propagator. We have 2 options here: the Kepler, which is a 2-body propagator, or a numerical high precision propagator. Let's do numerical high precision. We wait for the orbit to be propagate. We can see the sun vector when the simulation starts, so we can see that we have a very high beta angle in this case. We see the flag for the sunlight, so in this case the spacecraft gets in the night for a short amount of time, then goes back to sunlight. Here's the altitude. We are over 64 approximately kilometers above the surface. Okay, let's move on to model the spacecraft. So the options here are from 1U to 16U. Okay, in this case, let's do a 6U. So here we have the spacecraft. It starts with all the surface as an aluminum polish type of surface. So we can select for each phase one type of surface material. We can also define the altitude that we want to fly the spacecraft over there. This app only consider fixed pointing altitude. So in this case, the nadir X plus face is facing the moon surface, and we have the Y plus on the ram direction. We can maybe do Z plus for the ram direction, so we are flying with this big face. So let's select some options here just to give us an idea. Let's run like this. The X plus gonna be, let's do Z minus as a nadir. Okay, and the X plus, we're gonna fly like this. Let's put a solar panel on the Z plus face, so we can, here we select all the faces, Z plus, let's do a body fixed. So surface type, we have black coating, which has 0.96 of observativity, solar observativity, and 0.91 of IR emissivity. We can select also for a white coating, 0.2 observativity and 0.92 emissivity, solar panel, or MLI, or custom. You can also put your numbers for observativity, emissivity, and also specific heat. Let's do solar panel to see. We can also deploy some solar panels here to increase. So let's do on the Y minus, we can do some fixed wings. We can select the hinge where we want to put this wing there. So we can see we can increase our panel size. Let's also do the same thing for the other one, 3 panels. So our spacecraft looks like this. Okay. You can see that I select the fixed option. We can also do tracking. So let's do tracking. Let's see. So do tracking. So both of those deployable wings going to be tracking the sun. The Z minus, since we are seeing the moon and the moon has a very high IR emissivity, we can maybe select white coating. Maybe not a good option actually. Let's do MLI, reduce the emissivity and therefore the IR observativity. Okay, we can also, let's put on the X minus, let's do some radiator here. So maybe white coating here. On the X plus, also white coating. Okay. Moving on here. So one thing that I forgot to mention is when you put the solar panels, you also can put the cell efficiency. Right now I'm considering 28%, and the packing factor. Packing factor means that from this area 60% of this panel area is considered solar cell. So that's for calculating power. Okay. Moving on here for thermal parameters, we can see that the body mass, so the mass of the body of the spacecraft, start as a default as 8 kilograms. We can increase, like say 10. The internal node to total mass ratio, that means so this app use 7-node approach to do this preliminary thermal analysis. So we have to select how much thermal mass is on the internal node versus the faces. So we can simply do by this. So let's say 60% of 10, which is 6 kilograms, is the internal thermal mass, and the rest of the mass, which is 4 kilograms, is spread around the faces proportionally to their areas. Okay, that's the internal node of the specific heat. That's pretty much the number for aluminum. Then we move here to estimate our thermal resistance. So as we can see here, the tool already gives us an estimate for those values. So the Rx plus, which is the internal node to this face and to the back face, is considered to be approximately 10 Kelvin per watt. You can choose other numbers if you want, and that's really important to define how the heat is going to be flowing inside the spacecraft. Let's move to the power here. We can select 2 types of internal power dissipation. One is constant, so let's assume like 2 watt, Let's refresh this. So 2 watts constant during the 12-hour, or we can do day and night. So let's say during night we drop to 1. So it's going to be like this. It gives us our average power consumption. So let's compute power and let's see. Okay, here we have this spacecraft generator is generating on average 23 watt. That's the power generation profile during the day. Here's the battery depletion. So considering how much we are consuming, how much we are generating, we can see how much we are depleting during the night. So this is useful for you to properly size your battery. So let's take a look on how things are moving. So on this animation here, we see the panels tracking the sun, and we also can see when the active areas are illuminated by the sun, gets this bright red color. So we are generating power here. We can see on top how much power we are generating. So in this case, you can see that we are not considering the shadow, right? One option here is run, considering shadows. So the two then taking into account the shadows projected by the body. So you can see that that drops the power generation to 17 watts. Let's take a look again on what is happening and how the shadows are being casting. So we can see shadows appearing on that right wing because of the body. So these two can also calculate that. So in this case, for example, we can see that we have a very big area of the solar panel, of this body fixed solar panel, and of this wing panel being on the shadow, so not generating power. Okay, let's move to the thermal tab and finally calculate the temperatures. So let's compute thermal. So on this left part here, we're gonna be seeing all the thermal inputs. So solar radiation being absorbed, IR radiation, and albedo, which is the solar radiation being reflected by the planet's surface. Okay, and here we have, as we can see, the solar radiation being absorbed. This is the total. We can see by phases. So we can see that Z plus phase gets the most of the solar radiation, which makes sense since it's this top phase here is the Z plus. Here we can also see the IR radiation being absorbed, radiated, and or both. You can see both. On this case absorbed, we can also see phases. If it's hard to see, you can start clicking and see. So the X minus and the X plus is getting most of the IR radiation from the surface, which makes sense since we paint them with a white coating. And we can see that the gradient gives us this kind of profile as we are flying closer to the illuminated part of the moon. Here's the temperature of the internal node, dropping from the initial temperature, which is 27 degrees Celsius or 300 Kelvin, and all the faces temperature are plotted here. And you can also have the option to export all those results to your MATLAB workspace, and you can plot those values in any other way that you prefer. You can also save the simulation to be open later. So that's it. We have run a power analysis for the CubeSat considering shadows, and we also run a 7-node temperature simulation here.